In Conversation.
Hi everyone, welcome to the premiere episode of In Conversation with Abhinav Seetharaman. Today, we are outside the National Institutes of Health NIH campus in Bethesda, Maryland, where we will be speaking to Dr. Francis Collins, who is the director of the NIH. It is an absolute pleasure to have you as our premier guest on In Conversation, and thank you for being with us today.
Glad to be here.
So, you went to UVA for undergrad, and then Yale for your PhD, and you matriculated into UNC Chapel Hill, where you obtained your medical degree. So at what point did you decide to channel more of your efforts from actually practicing medicine into biomedical research? And what in particular drove that decision?
Well, you've already outlined what must be, to anybody watching this, a very nonlinear pathway. Because no one could say I had it all figured out.
Right.
I started out thinking I was going to be a chemist because chemistry is what got me excited in high school. I had an incredible chemistry teacher and taught me the excitement of how you could bring science to answer questions, solve mysteries, and I thought, that's what I want to do. So I went to UVA, which was my state school. I grew up in the Shenandoah Valley, Virginia, and majored in, guess what, chemistry. I didn't think I wanted to spend any time on biology. It was much too messy. I liked, well-orchestrated, sensible, equation-driven understandings of chemistry and physics, and that's what I stuck to. And after finishing that, wanting to extend myself a little further, went to Yale to get a PhD in physical chemistry. My work was mostly in quantum mechanics, solving second-order differential equations, which were mostly unsolvable. But at that point, I realized maybe I'd narrowed my horizons a little bit too much, and I began to hear noises that there are things happening in life science that sounded pretty intriguing. Recombinant DNA was being invented at that point.
Right.
And I had totally missed that because I had kind of intentionally stayed away from life science, and I didn't realize just how incredibly compelling it was once you started to dig into what was turning up about DNA and RNA and the genetic code. Gosh, life makes sense. I didn't think it was going to, but it did.
Right.
And I began to realize that is really calling out to me for something that I might want to do. So what to do? I decided I was going to completely reinvent myself, and I wanted to do so in a fashion that left all the options open about what kind of life science I'd get engaged in, including patient care. So I went to medical school.
Right.
That's the transition to the University of North Carolina, which is a great place to go. But once I got there, I began to still feel this urge about some kind of research activity, and genetics emerged as the sort of perfect place to put this all together. It was the center of the center of living forms, the instruction book for humans and everything else. But it was also sort of mathematical and sort of digital and satisfying to my brain that liked that kind of quantitative, rational view of science. So I decided, okay, I'm going to be a medical geneticist, whatever that is. There weren't a lot of people at that point saying those things. And that's sort of how it turned out. I did really want to learn medicine, so I went all the way through medical school, and then I did an internship and a residency in internal medicine. I even took an extra year as a chief resident to try to really tighten up my clinical skills and my ability to think about how to managing things. And then realized if I'm going to be a researcher, I still need to understand how to do experiments in molecular biology, not just read about them. So there was another 3 years interposed there of a fellowship back at Yale, where I learned really how to do a lot of the exciting things one can do with DNA and RNA, or at least you could at that point 35 years ago. Finally, after all that, I got a job, a real job, at the University of Michigan. And to answer your question about practice versus research, I guess I just try to do all of that. I love taking care of patients, so I continue to take care of patients, sometimes general internal medicine, sometimes patients who had genetic disorders where I might be able to have some special input, and it also gave me some really good research ideas.
Right.
I set up a research lab. I taught medical students, which was something I enjoyed. Sort of the triple duties of an academic professor of medicine. And I really liked that a lot.
Right.
And again, the patient interactions, taking care of patients with cystic fibrosis, patients with Huntington's disease, patients with neurofibromatosis, those all then became research projects because it was clear there was a lot of need to try to understand what was causing those diseases and what could we do about it other than just describe them.
Got it. Makes sense. And I remember in our previous conversation, you mentioning that at UMich you were the professor of Dr. Sanjay Gupta, which
Yes.
is quite fascinating. It's a
He
small
was just a regular medical student in the class, but all the medical students at Michigan for that 10-year period had to put up with me because I was the one who co-taught the course on medical genetics. And for the most part, I think they kind of liked it because I brought patients to class and sort of made this seem like it was relevant to these budding physicians when a lot of the time they were just being asked to cram facts into their heads. And genetics is so compelling. When you see what happens to somebody who maybe just has one letter out of place in that 3 billion letter genome and what that can cause as far as an illness and what we might be able to do about it, you can't sort of get your head around that without getting excited.
Definitely. And speaking of genetics, you oversaw and led the Human Genome Project in the 90s and 2000s. So what was that entire experience like for you, and what were some of your favorite moments from it?
It was another part of the unpredictable trajectory of my career because I never dreamed I would be asked to do something at that scale. Again, there I was at Michigan doing some research, having some success finding genes that cause diseases like cystic fibrosis. But it was really clear to me and anybody else at that point who was looking at the situation that we were not going to make much progress unless we had a well laid out, publicly accessible reference genome sequence for humans and some organisms that we could learn from as well. And that's what the idea was for the Genome Project. People today have forgotten, back then in sort of the late 1980s, most of the scientific community was opposed to this project, seeing that it was probably technically impossible to be able to do DNA sequencing at that kind of scale. And they were afraid it was going to take a lot of money, and the money would go for this and not for what they wanted. So there was a little competition there. So I was a fan of the project, and when it got started under the leadership of none other than Jim Watson of Watson and Crick fame, I was happy to go anywhere and talk to anybody about why this was such a great idea. And one of the first 6 genome centers was at Michigan, and I had the chance to lead that, and I thought, okay, this is going to be fun. And then things kind of didn't go so well, and Watson got fired, having relatively little control over what he says to whom, apparently. And that was like devastating. The project just getting started. This is like a baby in the crib, and suddenly there's no daddy and mommy, and what are we going to do?
Right.
And I did not expect the call would come to me saying, you should apply for this. And I resisted the idea because it seemed so out of sync with what I thought my own calling was, which was to be this academic, taking care of patients and doing research. But it was pretty hard to say I'm not interested, although I did say it a few times. Ultimately, I had to sort of recognize that there was probably only going to be one Human Genome Project. It might fail, but it might actually succeed, and to have a chance to be able to lead that effort. I was going to turn it down because it wasn't convenient. It wasn't part of my plan. There's a message there, and I hope anybody listening to this YouTube conversation will take that to heart, that sometimes the things that come along that would be really amazing to do are at the most inconvenient time, and they're most unlike what you thought you were going to be doing.
Absolutely.
But that's the way life is, and sometimes you got to pay attention and say, okay, sure, I'll blow up my plan completely, and I'll take a chance because this, if it works, it's going to be amazing. So I came here, I plunged in, I tried to recruit as many smart people to come alongside and work on this. We worked on model organisms first, and then we began to build up the capabilities to do this for a really complicated genome like humans.
Right.
And it was an amazing team, and it meant I had to become the leader of 20 laboratories in 6 countries, because it was an international project. But I only really had financial authority over some of them, the ones that were funded by NIH. The rest, it was sort of cajoling.
Right.
But that was okay. Every Friday at 11 o'clock, I still sort of have like this jolt on Friday, 11 o'clock. Oh my gosh, it's time for the call. We would always have this international call where we would go over in detail what each of the groups had been able to achieve in the preceding week, because this had to be run like a real industrial enterprise. And we had bumps along the road. Some of the people involved had substantial egos. They weren't used to being responsible to anybody except themselves. But we worked through it all because it was so compelling. You couldn't be involved in this without feeling the sense of history. And that carried us over some of those rough spots. There were rough spots when a commercial enterprise suddenly popped up and said, we're going to do this, and the government can basically step away because we can do it faster, better, and cheaper in the private sector. But by the way, we're not going to make the data available, at least not for free.
Right.
And that was a potential really serious threat to how this all would have turned out. Because the data, it's our human genome. It's our shared inheritance. We ought to all have access to it. Fortunately, after a little bit of tumult there over a year or two about a race to the finish line, the finish line was achieved. The public project achieved every goal that we ever intended to, and gave all the data away, not just at the end of the project, but every 24 hours, just putting it up there on the internet so people could start to use it. An amazing experience. And of course, I had to say at that point, this is great, it's a lot of A, C, G, and T in a particular order. What the heck does this mean? We don't know how to read this language. Now we've got to build on top of that with a whole lot of other projects to provide function. And that quickly became the focus for the next several years as I continued to have the privilege of leading the genome research effort here at NIH.
Absolutely, and I believe the project's completion officially was 2003, right?
That's right.
And that was also incidentally marked the 50th anniversary of Watson and Crick's
It was
discovery.
very timely. It was
So-
even the same month. It was
Yeah.
April of 1953 when they published, and it was April of 2003 when we were able to say we're done.
Wow.
Although we're done also meant, and now we have to get started on the functional parts,
Absolutely.
which we're still in the middle of.
Absolutely. And so I want to transition from here by talking about your work with Progeria. And you and your lab made the huge discovery about the mutation in the lamin A gene, which really causes progeria in the first place. So what initially got you into progeria research?
Like most things I've ever worked on in the lab, it started with a patient named Meg Casey, who I knew when I was a fellow at Yale way back in the 1980s, who had a diagnosis of progeria, which is this dramatic form of premature aging.
Right.
And I wanted to take care of her, and I wanted to do the right thing, but it was such a mystery, and the disease was so rare, there was almost nothing written about it. And I thought, well, someday, it would really be nice if somebody figured this out. Almost 20 years later, it was my lab that figured it out, and in that case, driven particularly by meeting another patient, a little boy who at the time was 2.5 years old, Sam Burns. Sam's parents, Leslie Gordon and Scott Burns, came to see me because they're both physicians. Leslie was an MD PhD, and here they had this child who was given this diagnosis, and they wanted to see something done to try to understand the cause and maybe even to come up with a treatment, knowing that otherwise this child faced a survival of about 12 years, which is the average survival for kids with this disease.
Right.
And it's particularly tragic because these kids have normal brain development. In fact, in my experience, they're all kind of precocious, but their bodies are aging, and they lose their hair. On the outside, they begin to look like little old people,
Right.
but they get heart attacks and strokes, and that's what kills them before they even quite get into their teen years. So a heartbreaking situation, one that cries out for an answer. And initially I started out by advising them about how they could get some researchers to work on this, and after a while I decided, well, why doesn't my lab work on this? Maybe we can help.
Absolutely.
And yeah, we did find and then published. Also in April of 2003, there was a lot happening at that point. the cause of this, which was breathtaking, because it was just one letter out of those 3 billion, where a C became a T. And every child with the classic presentation had exactly that change, but their parents didn't. So this is what you call a new mutation, a mistake that was made in that one letter in passing DNA from parent to child,
Right.
which then resulted in this devastating outcome. And it was in a gene called lamin A, about which a lot of work had been done, and that helped us. We didn't have to start from scratch. We could build on the work of others and almost immediately at least have a hypothesis about why this might cause cells to senesce prematurely, and that was reflected then in what happens with these kids. So yeah, within a few days after knowing what the mistake was, we had a hypothesis about what the cause was and some ideas about what might be done. And with lots of support, and Leslie Gordon became a partner in this research and continues to this day to join all of our lab meetings, we are able to, just in 4 years, start a clinical trial. And that's really, I think, a new record almost for going from gene discovery to clinical trial. That clinical trial has clearly shown benefit. Kids with progeria have, in general, been able to live several years longer with this treatment. That includes Sam, who was one of the first kids to get into the trial. Sadly, Sam died a couple of years ago at age 17, and what a loss that has been. And anybody who's watching this and who's therefore on YouTube, just go and look up Sam talking about life according to Sam, or look up his YouTube, his presentation in a variety of ways. There was a whole HBO film on it,
Right.
Which was pretty dramatic. He inspired us all, and
Absolutely.
maybe we helped him, but not enough. So we're not done here. We need to come up with better ways to add to what's already been done, and my lab continues to be deeply engaged in that, now with the idea of going even more precisely to fix the problem using gene editing, which is, if you can make it work, the way where you don't just manage something downstream of the problem, you actually repair the DNA mutation. That sounds like science fiction, but it's getting closer all the time.
Absolutely. And speaking about Sam, millions around the US and the world know about his story, have heard his story, and are inspired by that story.
Yeah.
What was your favorite moment with him, or a favorite recollection of him?
I guess I had the chance to give a talk at TED-Med about the development of treatments for rare diseases. And this is one of those things that ends up with hundreds of thousands of views, because it's very much watched as it sits there and archived over years.
Right.
And I thought I could talk about this in a scientifically interesting way, but it'd be a lot better if I had somebody come and describe what it's like to be on the receiving end. So I invited Sam, and he came down from Boston, skipped school that day, and came up on stage in the middle of this to tell his story about how being involved in a clinical trial, having this kind of new drug development for a really rare disease, what that had meant to him. That was a special day.
Absolutely. And moving on, in 2007, you were bestowed with the U.S. Presidential Medal of Freedom, which is the highest civilian award of the U.S. So what was your initial reaction when you found out that you would be a recipient, and what were some of the emotions going through you as you were being awarded with the medal on the stage?
That was just astounding. Again, never imagined such a ceremony with the president presiding, bestowing these medals on people from a wide variety of perspectives, from the arts, from military heroes to authors, and then, this science guy who had worked on the human genome. It was a remarkable day, and of course I had to say, in every way, I was standing in for the thousands of people who had worked together,
Right.
not worrying about who would get the credit, to get that genome sequence done, 2,400 of them who all selflessly put themselves into this remarkable historic goal and made it happen.
Wonderful. And just 2 years later, in 2009, you were appointed by then Pope Benedict XVI to the Pontifical Academy of Sciences. So could you tell us more about this experience? Sounds fascinating.
Pontifical Academy of Science has been around for a very long time. It is located at the Vatican. It is a place where they bring together people to talk about science and faith and how they might relate to each other. I had written a book in 2006 called The Language of God about my own conclusions that science and faith actually have interesting things to say to each other and can be seen as quite harmonious in terms of providing different answers to different questions. And that is a path I arrived at from, again, a rather indirect way, starting out as an atheist and ending up as a believer. And so Pontifical Academy has conversations of that sort. I was glad to be invited to join that group for a deep discussion that involved people like Stephen Hawking, and afterwards then got invited to be part of this Academy of Sciences, which is an interesting group. And I would say probably less than half of them actually believe in God. It's an interesting academy to have pontifical in front of it, but it provides for the kind of conversation that might not happen too readily in other places.
Absolutely. Wonderful. And as we continue to make discoveries every day, and as technology continues to improve, where do you see healthcare technology in the next 10 years and perhaps even 25 years from now?
Yeah. It's a very exciting time right now. I was asked to come back by President Obama to be the NIH director 10 years ago, and then kept on by President Trump. And it's an incredible privilege to stand and lead this $39 billion a year enterprise, the largest supporter of medical research in the world. But it also gives me a chance to look across the whole landscape and see what's happening and what's coming next. In the next 10 or 20 years, my goodness, we will figure out a lot of things that are currently mysteries. We'll figure out how the brain works. That's going to be pretty amazing. Definitely. We have an organized effort to do that. How do those 86 billion neurons between your ears do what they do? And how do the circuits that are in there carry out these remarkable functions? That's pretty ambitious to imagine that our brains are complicated enough to understand our brains, but I think we're going to get there.
Absolutely.
And that will have all kinds of consequences for diseases like Alzheimer's and Parkinson's and schizophrenia and autism, which we desperately need to understand better. We'll make great progress in cancer. I think right now we are seeing the emergence of this immunotherapy approach for cancer after many years of frustrations, where now it's really starting to work and is working dramatically for some cancers and ought to work ultimately for almost any cancer if we can figure out how to be smart enough about it. So that's a big deal. We will be figuring out how to, for rare diseases that are caused by these genetic glitches like Progeria, how to go in and actually repair that damage using CRISPR-Cas and the gene editing systems that are just coming to light just in the last 5 years and now seem to be poised for this kind of therapeutic advance. I think in the next 5 years, we should be able to cure the first molecular disease, sickle cell anemia, using this gene editing approach, and give those people, 100,000 of them in the US and millions worldwide, not just a treatment that works, but a cure at the most fundamental level. I couldn't have imagined saying that 10 years ago, and now I'm saying it with a good deal of confidence.
Absolutely.
So anybody who's listening to this, who's sort of trying to figure out, hey, what do I want to do with my own pathway? This is an amazing time to get involved in medical research, because we are going to figure out mysteries and come up with interventions that are going to save countless lives. And that, how could that be more exciting than this, to have a chance both to do great science and also to see what a human impact you can make?
Absolutely. And I'm sure many in our audience will be inspired to take up what you just said.
So we need them. They should hurry up. It's a lot to do.
Yeah, for sure. And I know you serve and continue to serve as an inspiration to so many around the world, and especially to youth and young adults who are interested in pursuing careers in STEM and study STEM-related subjects, STEM being science, technology, engineering, and math. So nowadays, however, we are seeing a decline in the U.S. in youth interest to pursue STEM-related subjects and careers. So what, in your opinion, are ways in which we can reverse this trend, or at least work towards it?
Yeah, I think part of it is just we haven't done a great job of really sharing how exciting this can be as a career path. Science is often not particularly well taught in middle school and high school. It's often presented as sort of, you got to memorize this stuff and take the test.
Yep.
That's not what science is about.
It's speaking from personal experience.
Yeah, exactly. You have this. That's why I got turned off by biology. It was taught that way. You can look all that stuff up. We have the internet. You don't even memorize this stuff. You need to kind of get your head around the principles of what's going on and to see how technology, coming from all sorts of directions, robotics, computer science, nanotechnologists, engineering, it's all kind of coming together in a way that allows us to view life science in incredibly interesting ways. I don't think that's coming across very well. Maybe programs like this can help a bit with that. We need to do a better job of sharing that.
Yeah.
And there may also have been a sense that maybe this wasn't a good time to be a scientist. Things have been a little tough in the US as far as the support for science. I'm happy to say over the last 4 years for NIH, we really turned a corner. Support for NIH has gone up by 30% in the last 4 years. So there's a lot that we can do, and a lot of young scientists who are getting the kind of support that they were hoping for. It's a really good time to come and get on board. And how do people make decisions about how they want to spend their time? What are you really looking for? You want a career that has meaning, where you feel like you've contributed something, where you made a difference. And there are ways to do that, but science is a pretty powerful one. You are contributing something to knowledge, and for life science, no matter what you're doing, there's something about it that's also contributing to somebody who's out there hoping for an answer to an illness that hasn't been figured out yet. How could you say no to that?
Definitely. And what are the qualities, in your opinion, of an extraordinary scientist or researcher?
I think curiosity. You're always trying to figure out stuff that people don't know answers to. It helps if you also are willing to take some risks and tackle hard questions, not just sort of the obvious next step, but something that's a bit more profound. You do need to work well with others, because science maybe was once a lonely enterprise, working 2 a.m. by yourself in a lab. Not anymore. It's very much a team enterprise, and the things that happen that are most exciting is when you bring together people with different expertise and do something that none of them could have done by themselves. Scientists these days need to be pretty sophisticated about computational approaches. An awful lot of science now depends on being able to code and being able to deal with big data sets. But I think a lot of this current generation is unafraid of that as compared to some of their elders. And I think also a willingness to say that this is maybe not about being the richest person in the world, because science isn't always that profitable, but you'll do fine. But it's about finding meaning to what you're doing. Put all that together with a generous dose of willingness to keep your horizons wide open and don't get too narrow too soon, and then you've got a great scientist.
For sure. And I want to conclude by asking a two-part question. The first part being, who are some of your favorite science authors and writers? And to the youth and young viewers in our audience, what are some of the books or authors you would recommend to them to really get them more interested in STEM?
Well, there is an increasing number of good science books that are out there. We at NIH run a program every year called The Big Read, and I get to pick the book that we're going to focus on. And people will read it, and then we'll bring the author here, and we'll have a discussion about what it was they were trying to talk about. One that I think might be, if people are interested in cancer, The Emperor of All Maladies, a remarkable book about cancer.
By Siddhartha Mukherjee.
Yeah, by Mukherjee. And then his subsequent book, and he was our big read last year, called The Gene. So it's really going through the story all the way back to Aristotle and up through Mendel and on to now and the future. Pretty remarkable book. This year we had Ed Young talking about the microbiome, which was also a wonderfully well-written and intriguing book by a very capable science writer who writes for The Atlantic. So yeah, there's a lot of stuff out there that's worth getting your head around. And there are people writing books about precision medicine. I wrote one once called The Language of Life, which goes through why it is that you want to know about your own DNA and how you could use that information. It's not hard to find. Unfortunately, I think many of the books you find on the bookshelf at the present time in most bookstores, because I go and look, tend to be ones that have been around for a long time and may not have really kept up. So find things that have been published in the last few years, and there's good stuff there all around.
Absolutely. And I know you're an avid guitarist and vocalist, so right as we conclude, I want to tell our viewers to please check out Dr. Collins' song on YouTube, Amazing DNA. If you really either want to quickly learn about DNA or if you're continuing your passion for the STEM fields. So once again, thank you so much for your time, Dr. Collins. It's been a pleasure, and I'm sure that our viewers and audiences around the world will continue to think and study science.
Well, thanks for the conversation.
Thank you so much.